Okay, thank the organizers for continuing with this wonderful discussion meeting, and I'm very happy to come here again. Now I'll be talking about the free energy profile of complexation of two oppositely charged polyelectrolyte chains. The work has been done by Shomik, who is in the audience. He has given a poster. Some of you have been to the poster. Now, this is the basic problem. We have a polycation and a polyanion with the oppositely charged counterions, and they will eventually complex in equilibrium. That means the polycation and polyanion, the monomers will form bound ion pairs, and the counterions will be free. That has been observed for a long time in polymer physics or charged polymer physics. Now, there can be many different energy contributions, energy or entropy contributions to this process. You can think of once, for a single chain, some of the counterions will be condensed, some of them will be free. And for the condensed counterions, there will be entropy of sliding over the chain. And then, of course, the entropy of free counterions, like the ideal gas entropy. Slightly more complicated, but of the same nature. And there are fluctuations like screening, and of course this electrostatic energy of all bound ion pairs. We will be following a two-state model in which either the counterion is bound, forming a bound ion pair, or it is free, enjoying the entropy. And of course, finally, you have this configurational free energy of the polymer chain, which is there for uncharged chains. Without any other interaction, the monomers will do random walk. It will be a Gaussian chain. With self-avoiding walk, it will be a Flory chain, and then with charge, it can be anything, because charge interactions are long-ranged. So the major questions which we are trying to answer here is what are the major forces and factors that lead to complex formation. So of course, the complex is forming. There are so many components of the energy. So is it the entropy gain due to the counterion release? Or is it the energy of the adsorbed monomer pairs, energy gain due to for the monomer pairs? And is the whole process of complexation energetically downhill always? That means given the known ambient conditions like temperature, dielectric constant of the solvent, things like that, is the process always downhill? That means will they always form a full complex, or they will stop at some point of time forming the complex, and the rest of the counterions will be free, and the other monomers will also be not the polycation and polyanion monomers will remain free. So the question is what happens actually following a theoretical analysis. And then finally, of course, identifying the dominant contributions to the entropy and enthalpy, and then trying to answer this question that this complexation process, how does it depend on temperature? Now again, I'll go back to the very simple description of the system where this is a polyanion and you have this positive counterion. So you can have salt as well. In this talk, I'll ignore the salt. Then this is the basic premise which I have already talked about. You can have this energy gain due to bound ion pairs, just simple Coulomb energy. And you can have these free counterions, which will give you entropic gain to the system. And this competition between these two processes, these two parts of the free energy, will determine how many of those counterions will be adsorbed and what will be the average charge of the system, of the polyelectrolyte chain. Now, there have been a lot of work on this. The most famous theory is the Born-Overbeek theory, but these theories are a little bit different from what we will be doing, because they will consider rather a uniform kind of density, like Flory kind of density for the system, and they will look at this, for example, this is a very recent experiment. They will look at this phase coexistence of the complex. One side is the polymer rich phase where you have the complexes of several polymer pairs. The other side is polymer rare, that means not much amount of polymer, things like that. So that's basically a Flory-Huggins theory of where you have many polycation and polyanion chains in the system. And generally for two phases, the densities will be uniform. Separately, two different values, but uniform. Then we look at these simulations. There have been many of those. I have just cited one, that they consider only two chains, the way we want to do here, and they could see that these the oppositely charged chains, they actually slither on each other, the monomers, and they slowly form these bound ion pairs, and the counterions become released. Because once they don't have their monomer to absorb upon, they will be rather released, that because they can enjoy the entropy. And finally, this kind of a complex can be formed. So what we do here, we, of course, I'm doing a theoretical analysis. We are taking a polymer chain, two chains, polycation, polyanion, there are counterions, and then this is an intermediate step. When some of the monomer pairs have been formed, so the green and the red and the green, two of them will form a black pair, and this will be basically, in first order, it will be an uncharged globule, right? For an uncharged globule, well, there are theories which will tell you that there will be a collapse. At this moment, we are not looking at the collapse. We are just looking this globule as a Gaussian chain. And then I have a polyelectrolyte this side, another polyelectrolyte. Of course, the number of monomers are less by the number of monomers which have formed the bound ion pairs. This is the model, uniform expansion model. I'll very quickly go to the free energy. It's known to some of you. It has been extensively used for a single polymer chain or polyelectrolyte chain. Now, there are several parts to this. I believe there's no point in really getting into this. You have this F1 is the charge of each of the chains, because the chains are equivalent, just the charge is opposite from symmetry. F1 will be same with an opposite sign, and it's the fraction of monomers which have been compensated by the counterions, 1 minus that. So it's actually the effective charge. Then N1 is the total number of monomers. Small n is the number of monomers forming the bound pairs. There are other, this F2 term is the free energy of the counterions coming from entropy. F4 is the bound ion pairs. This is the Debye-Huckel term. This is the inverse screening length. And now this F5, 1, 2, 3, 4, 3, these are the different parts of the chain free energy. This is the Edward Hamiltonian. It comes from the Edward Hamiltonian, but it includes the screened Coulomb interaction, and that gives this free energy part. This part gives you the Gaussian chain, and this is L3. L3 we call this L tilde. L tilde goes as Rg squared in general. So this L3 actually gives you the size of this, but we take it to be 1 for Gaussian. L tilde is 1. So because I have told you, because we will take this as a Gaussian chain, and then there are some other factors. Finally, they are all functions of this screening length, which is again a function of the charge, free counterions, number of monomers, and the expansion factor. Now, and of course, we have to add one more term here, because two sort of charged spheres are interacting here. We have taken a DLVO kind of potential for this. So what do we get here? This lambda is the overlap parameter. That means how many of the monomers have formed the bound ion pairs. It can be 0 when they are separated. It can be 1 when the entire thing is black. All of them have formed taken part in the globule. This is the charge. This is the expansion factor. This is the actual radius Rg square. It will of course go down, because the size of the polyelectrolyte which has not complexed yet, the size will definitely go down with this overlap parameter. It was possible to find, out of all that mess, it was possible to find an analytical expression for the charge, which we did before for the single chain as well. Here lambda will be, if lambda is 0, we go back to our old expression. It's you can see it's the function of the overlap and the density of the monomers. Delta is some kind of a dielectric mismatch parameter related to the dielectric constant, Lb tilde Beerem length, most of you know. So we could get that. These two terms are not so important. You'll see these numbers are of the order of 1000. You'll see why later. This is F1, the entropy due to sliding on the chains. F3 is the Debye-Huckel, this fluctuation term for free counterions. And then these are the two competitors we have been talking about. This is the entropy of free counterions, and this is the energy gain due to bound ion pairs. You can immediately see entropy of the free counterions always will be favorable. It gives a gain in free energy after complexation. So 1 is complexation, 0 is total separation. So it always goes down, but you can see that the ion pair formation, it can be the opposite direction. For particular values of Lb tilde. Lb tilde is actually temperature. It can also be dielectric constant, but we have taken water as a solvent, so we keep the dielectric constant as constant, and the temperature we vary here. So for Lb tilde 5, so Lb tilde is inversely proportional to temperature. For very high value of Lb tilde, temperature is low. For low values of temperature, I have 1 minute. 1 minute for talk or question also? Okay, great. So very quickly I'll tell you this, that you can see that, no, that part I cannot get into it, I don't have time. And the other terms are actually not so important. This is the Dlvo term, this is the entropic term for the chain itself. This is the Gaussian or expanded or Flory kind of thing that comes from here. So finally what we can see that this is the total free energy. This is what we wanted to get at. You can see free energy gain after complexation, that is monotonic with overlap. So we could not find a range of any set of parameters for which it is going in the other direction. So it is always energetically favorable. The other thing, more for moderate temperatures, these intermediate values are moderate temperatures, the difference is more, and for extreme temperatures the difference is less, difference from this point to that point, the value of the gain in free energy. So this is what we have found. Some more work has to be done also. So I have already talked about the things. So basically what we see, the counterion, the entropy gain due to released counterions is the major and unfailing driving force for polymer complexation. Thank you.